So, we continue with our just previous lecture where I talked about some of the VLSI design automation steps. So, in this part 2, we continue our discussion and look at some of the other steps which are also very important in the physical design cycle. So, we start with static timing analysis. Okay. Before going into what static analysis or timing analysis is, let us look at a design from a general perspective. See, when we create a design, we have some design specifications to meet. Typically, design specifications may mean that I want to run this circuit at a minimum clock frequency of certain things, maybe you say 600 megahertz. This should be the minimum clock frequency. This should be the maximum possible delay between input and output lines. A few such things can be there. These are timing related constraints which has to be satisfied to qualify a design to be satisfiable with respect to the specifications. Now, what might happen is that once you go through the design process, you arrive at a design which is correct in terms of functionality, but what you find is that delay wise it is not performing as per your expectation or requirement. You see, the CAD tools, the tools that you are using for translation, Synopsys, Cadence, Mentor Graphics, whatever you use, those are extremely complex pieces of software, and you can never expect that whatever they are generating will always be the best possible or will be able to meet your requirements all the time. So, you need to continuously interact with the tools or the systems in order to assess or judge the kind of design that you are getting. Now, static timing analysis is a very important step in this respect, because of the simple reason is that today we are talking about circuit designs where we have very stringent timing requirements, real time requirements, minimum clock frequency requirements and so on. So, we must be able to analyze a circuit netlist beforehand, before going into the detailed fabrication steps, to assess whether we are going grossly wrong something somewhere. So, if so, we can take some corrective steps, we can modify our netlist, we can try to make our clocks faster in that way, and you can do something using some kind of worst case analysis. So, static timing analysis basically talks about that. So, this I have mentioned, it basically tries to analyze a circuit netlist to determine worst case circuit delays. See here, when you calculate worst case circuit delays, you not only consider the delays of the gates as some single numbers, like I can say to simplify thing that the delay of this gate is 5, the delay of that gate is 4, this is 3 and so on. Accordingly, I calculate the total delay, but things are not that simple. So, when gates are fabricated in the VLSI chip using the kind of deep submicron technology that we use today, there can be lot of variations in parameters. Like one gate can be having a delay of 5, while the other gate can be having a delay of 4.7, other can have a delay of 5.2. So, there will be lot of delay variations. So, we call it a design slack, some minimum value and maximum value. So, the gate delay has to remain within that. If we find that it is not within that, then possibly our circuit will fail, but that slack has to be considerate enough that taking care of the variations during fabrication, it should be lying within those regions. Similarly, rising time and falling time of the signals. So, maximum or the slowest rising and slowest falling times we have to take care in order to determine the slack values. Okay. So, this is one. Using this, you can estimate the worst case delays, and hence you can predict the maximum frequency with which you can feed the clock signal. Not only that, you can do some analysis on the circuit and you can suggest some circuit modifications, so that the circuit can run faster, the clocks can be made faster. As I said, this is an essential step in modern day systems. Now, let us take a simple example here. So, here as you can see, here we have a simple combinational circuit comprising of 4 gates. This A, B, C are the primary inputs, and this J and this other one D, these are the outputs. So, we can model this as a signal flow graph, where we use 2 dummy nodes in the input side and output side, and every you can say every signal line or every gate can be represented by a vertex. So, every signal line let us represent it as a vertex in this graph, and this dummy node here let us call it source, we label it NS, and the dummy node here, this is the final NF. At the input side we have nodes for A, B and C, here D, E, F. You see this E and F, apparently they represent the same line, okay? They are electrically they are equivalent, but suppose I want to model this interconnection, maybe these are long interconnection line. So, I use E and F at 2 separate nodes. Similarly, G and I, D and H, J, G like this. And in this graph I am not shown here, each of this edge can have a weight. This weight might indicate either the delay of the gate, delay of the interconnection, or both. Like for example, when you go from A to D, you go through this interconnection as well as the delay of this gate, then you reach D. But when you go from E to F, it is just interconnection, G to I just interconnection. So, if you model this signal flow graph, now I think when you model the signal flow graph, you have to have some realistic values for these weights. Now, once you have this, then you can have some kind of a shortest path or the longest path algorithms running through this graph, so that you can find out what is the longest delay between NS and NF, the longest delay. Now, suppose this entire circuit I have in a scenario like this. So, I am showing this circuit as a box, black box. So, A, B, C are the inputs, right. So, D and J are the 2 outputs. Let us suppose these are fed to some storage element, let us say flip flops, these are clock. So, this output can be going to some other circuit element which in turn is feeding A, let us say. Now, through timing analysis, what I can find out that in this circuit, the maximum delay from the input to this output D is, let us say, delta D. Then I can also see, I can evaluate that this circuit module which is available here, let us say the delta is delta. So, the clock signal that you are applying, if you look at the clock period T, T obviously must be greater than delta plus delta D. This is a hard timing constraint that this circuit like this will be having. So, if you do a static timing analysis of each of the circuit blocks between the flip flops, then you can have a very fair estimation of the worst case timing delay between clock pulses, so that you can know at least to a fair degree of accuracy that how much or what is the maximum frequency of the clock that you can apply, right. So, basically this is the main purpose of static timing analysis, but there are many other issues that we shall be discussing when we look into this topic in more detail later on. There are other issues like determination of false path, adjusting a circuit. Like for example, let me also tell you another thing. You can have a scenario like this. You have some combination circuit, then a flip flop feeding like this, then a combination circuit, then a flip flop. Maybe you have something like this, maybe something you are feeding back like here. Now, it is possible to move, say this combination circuit can consist of a number of gates. Now, it is possible to bring some part of this circuit along here or the reverse and move this flip flop a little ahead in the chain, because what we are trying to do, these delays of this circuits delta 1, delta 2, delta 3, if there is a mismatch, suppose delta 3 is significantly greater than delta 1 or delta 2, then delta 3 will be the dominating delay which will be determining the clock frequency, maximum clock frequency. But if you can balance this out by moving these flip flops forward and backward in the chain such that these deltas can become approximately equal, then you can carry out some optimization with respect to the clock frequency. Okay. So, all these things we shall be discussing later. And another important issue is considering signal integrity and crosstalks in circuits. Now, you see in a submicron VLSI chip, the gaps between the two interconnection wires are very less. Due to fabrication error, they can even come closer. So, because of that, if there is a signal transition on one line, that transition can get coupled to the other line, and if you are not careful enough, this can lead to an error in the calculation or computation which those signal lines are leading to. So, signal integrity means the signal what is supposed to be, but because of crosstalk the signal is getting, you can say, polluted, or there is some error introduced therein. So, you should be able to model, analyze this kind of signal integrity and crosstalk issues and come up with a set of approaches which if you follow, you are expected to overcome or eliminate this kind of problems in practical circuits. So, typically design rules are used which are quite conservative, but the advantage is that if you follow these design rules, your final design is expected to be free from this kind of problems. Design rule means you can say that the minimum separation of the line should be this. So, in all the lines that you are laying out, you make sure that the minimum separation should be this. Actually, this is just an example, and also another example can be, you can also limit the maximum length of the lines, because longer an interconnection line, the distributed resistive and capacitive effects can come in, which can lead to not only signal delays, but also signal degradation. The signal, if it is feeding to some other circuit, because of degradation there can be errors, means a 1 might be recognized as 0, something like that. Okay. So, let us take an example here. So, here we show some gates where some signal transitions are taking place at the output of these gates. The second gate transition is happening, this gate is transiting a little later than this transition. Because these two interconnection lines are running parallel to each other and quite close, let us say, there will be a capacitive coupling. Because of the capacitive coupling, so what might happen is that in this signal line, second one, you are expected to have a clean transition like this, but because of this rising sudden spike here, you can encounter a sudden noise signal injected here like this. And if this noise signal is sufficiently high in amplitude and this signal is feeding some other gate, so it might temporarily recognize it as a 0 and then again 1 like that. So, that might lead to a timing error and some error in calculation. So, this is just a very simple example I have given, but here we shall be looking at much more delay related issues and other problems therein in our next modules, where we discuss these things in detail. Okay. This clock I have just mentioned earlier, this clock and power routing requires some special attention, because when you have the clock signals, it is not just the issue of just allowing the signal to be distributed to the different points where it should be. There are a lot of other clock related parameters that need to be satisfied for correct operation of the storage elements: rise time, fall time, setup time, hold time. There are lot of such delay related parameters which need to be looked at very carefully, and if your design is good, those delays will also remain within limits. Okay. You have to take all of them into account so as to come up with a realistic value of clock frequency which is expected to run this circuit in a correct way. Okay. So, for clock routing, you need to consider issues like delays, skews and hazards. Earlier the example I took, we are talking about clock skews. Clock skew means same clock is reaching two different points in two different times, but by using that H tree kind of an approach, by making all the interconnection lengths equal, the interconnection delays are also expected to be equal. So, we are expecting to reduce the skew to a great extent. Okay. So, this is so far as clock is concerned, but for power routing with VDD and ground, this also is a very important problem, because one thing is that we should not want to mix the power signals along with the normal signals that carry data, because data variations must not couple into the power signals and generate power supply variations. That may not be acceptable. So, usually the power signals, the VDD and ground, they run on separate dedicated metal layers. So, interference and crosstalk are minimum there. Not only that, because of variations in power requirements in different parts of the chip, in some places the lines may be wider, in some places the lines may be required to be much less wider. So, the width of the lines is not fixed, unlike the signal lines. Somewhere where a lot of current is expected to flow, the line can be wider, later on the lines can become thinner and thinner and thinner like that, okay, as the power signals are getting distributed in the power supply. So, this would require a priori power analysis to be done to decide on the exact widths of these lines. Okay. So, this is the same diagram we saw earlier, clock generator, but as I said, in a real clock distribution scenario, the clock distribution points may not be so uniformly located. So, we can have a scenario like this, where the small crosses are the points where you need to distribute the signal, and maybe the clock is generated somewhere centrally. So, there are a lot of, here you need to do a lot of complex analysis in order to determine various parameters so as to reduce the clock skew in these cases. So, here we shall be looking at some algorithms on this later on, and related to VDD and ground nets, as I said, various segments can have variable widths, line width calculation is required, which is complex, and they are typically laid out on a separate metal layer. Now, the last thing that that we shall be discussing with respect to Vlsi physical design is a process called physical verification, that is followed by design sign off. You see, what is physical verification? As the name implies, we are trying to verify something through physical inspection. Now, you see, we have gone through all these steps of placement, routing, etc., etc. We have arrived at a layout, and once you arrive at a layout, well, those inspection you cannot see with your eyes, it has to be done in an automated way using an X-ray, using a microscopic mechanism. You have to look into the layout. You can look into the layout and you can find out anomalies therein. As I said, you can have some design rules, like two wires running parallel to each other must have a minimum separation of this. Now, I refine this a little bit. If the two wires are running on the same layer, separation should be this. If the two wires are running on two different layers, separation must be this, and so on. Similarly, minimum widths of the layers. If it is metal, what should be the minimum width? If it is polysilicon, what should be the width? Diffusion, what should be the width? If it is a contact connection, what should be the minimum dimension? These are some design rules which are defined a priori, and when you are creating the layout, there are a lot of optimization steps that are carried out. It might so happen that due to some bug in one of these steps, some of the design rules are getting violated. So, instead of letting those violations remain with your layout, it is always the case that you do a physical design verification to do some layout extraction, verify the layout overall, to look for some anomalies in those design rules, and only when you are satisfied with that, then only you can go for the so called design sign off, where you can actually send your this layout data for fabrication. As I said, this layout data is usually sent in some standard format for fabrication in the foundry. GDS2 is one such very popular format which is used. So, here as you can see, as I just now have said, because of the size and complexity of the designs, physical verification and methodologies are essential. See, sending a design for fabrication, sometimes we call it as taping out. Taped out is a term which is used very popularly in the design houses, and this physical verification is not a very well defined process. That is why it may require a number of iterations. These are more like some ad hoc checks and optimizations you are trying to carry out, some incremental fixes. So, in order to fix one error, maybe some other error might get injected. You have to do it continuously. So, and this is an iterative process which may need rechecking and retesting if required, as and when required. So, this is the last process that you need to be done, and you should be satisfied about it before you tape out your design for fabrication. So, as I said, design rule check is one process which is very important. Minimum width, minimum separation, same layer, different layers, minimum size of contacts, all these have to be specified. Now, these separations and these widths, these are typically specified in terms of the basic feature size, we refer to as lambda. So, as technology scales down, say from say 0.25 micron to 0.18 micron to 0.12 micron to today's say around 22 nanometer and beyond, then the design rules keep changing, but all the rules are in terms of the basic feature size lambda. For 0.22 micron, for 0.022 micron 22 nanometer technology, your lambda will be 0.022 micron or 22 nanometer. So, in terms of that lambda, that parameter lambda, you define the design rules and you try to verify the designs like that. Okay. And what we do is usually some kind of template based matching. You define a lot of templates, because just design rule checking may be difficult. You try to match those templates against the entire netlist by sliding a window kind of a thing. Like I am showing an example, like here you have a window shown by this red box. This red box has a something like this, say a zigzag kind of a connection, where some minimum width is expected, but due to some fabrication error the width of this line has been reduced. So, this is a design rule violation. So, you can have some inspection in the layout and try to find out whether such design violations do exist or not. So, these patterns, there can be different abstraction of different kinds of patterns. You move it and see that whether, I mean, what you see under this window is matching with any one of these. This is typically what is done, and just trust me that this is a very time consuming process, because you have to look through the entire layout. It is a quite time consuming process, but it makes sense because it is only after this you will be sending out your design for fabrication, which is again very expensive. You cannot afford to have any error before that. Okay. So once you are satisfied with this, you can finally send the design for fabrication, taping out, and you get your final chip fabricated after that. So, what we have seen is that we have looked at a very quick review from a very high level, a bird's eye view you can say, about the different steps that are required in the physical design process, which we shall be dealing with in much more detail in the successive modules. And another thing also that we will be discussing about is some special consideration about low power design, because low power design is also extremely important nowadays, because most of the computing gadgets that we use nowadays are operated on battery, other than the desktops on our offices, laptops, mobiles, tablets, they all operate on batteries. So, reducing the power consumption is of paramount importance. So, that is one thing that also we shall be discussing, and with this we come to the end of this lecture 6. Thank you.